And we are recording. Cool. So this week is confidence intervals. This is chapter 8 in the book. Again, I put things in a particular order here in the home page for a reason, because that's the order I want you to go through looking at stuff. And when you get to the practice, you're going to have to look back at some of these other things to kind of figure out some of the practice. But we'll get to a couple of those problems today. I'm going to do the critical thinking different this week. I'm still working on that. I'm trying to find a way to make that quicker to get you guys feedback. And then the application 6, I'm revising from what I did last year for a couple of reasons. There were several requests last week about the optional exercises I posted being extra credit. I usually don't like to give extra credit because I think I give plenty of other opportunities for people to improve their grade. But there's some wicked, interesting, cool stuff in this chapter that I am willing to give extra credit for. And so I'm kind of going to break the application into 2 parts. One part's the regular application, the other part's going to be an extra credit, which if you do, it'll be just extra points to add to your grade. And if you don't do, it doesn't matter. And again, hopefully I'll have that critical thinking revision and the application with extra credit revision done, hopefully tomorrow. And then I'll post details about that and record some information tomorrow about that tomorrow. All right, so let's get busy with the actual math. Read this right here. This is the goals for this week. I'm not going to read it for you, but I'm going to do a presentation that kind of covers that in just a moment. Vocabulary. So this is a quick snapshot of the new words and phrases that are going to come up in this chapter that you want to take a look at. And the key terms are always at the end of each chapter. Instead of linking to the web book, I have a link here to a PDF version of the book that I've marked up. It's still searchable, so I can go in here and type a Control F, and I can search for things like average, and it will find everywhere average appears. It even recognizes the text I wrote. So you can search for words I wrote too, which is kind of cool. I was pretty impressed with that feature. But anyway, so there's 2 reasons I'm doing this. One, you can see things I highlighted that I thought were extra important, right? So all of this is important, but these highlighted parts are extra important. And then every once in a while, I'm going to make a note that, we're going to skip this formula for now. We'll deal with it in weeks 9 and 10. And sometimes I just outright cross stuff out. Like down here, I just say in the next example, we're just not going to do that formula type stuff next. And you might know from before, I don't use a TI calculator. I highly recommend not going out of your way to buy one. They do statistics, but it's way more useful to learn how to use a spreadsheet. Because when you go to get a job, no one's going to care if you can use a TI calculator, but employers will be impressed if you can use a spreadsheet. So don't read the web book this week. Read my copy of the text that I've marked up. Because I specifically cross stuff out, and I also include some examples eventually of how we're going to do things instead of the book approach. The book has an approach which is pretty standard in statistics class that's based on a whole lot of theory and formulas. And those formulas, there's a lot of formulas to memorize and use. We're just going to pretty much use stackkey and arithmetic instead of those formulas. And in weeks 9 and 10, we'll come back and look at what those formulas mean. So first, we're going to just kind of do it through experimentation, all the stuff in chapter 8. And then in weeks 9 and 10, so 3 and 4 weeks from now, we'll go back and use the theory and all the crazy formulas. So in my note here, I say, hey, we're skipping these formulas in the book, right? So we're not going to do that. So it's important you, again, look at my version of the text, not the online book. We're going to be using stackkey. Whenever I read a book, I take notes on paper, and sometimes I type them up pretty. And so here's some notes I wrote as I was reading through the book, especially related to the way I'm going to do things. And if you tune in multiple times during the week, you'll see me covering this stuff, and I'll cover most of it today. And then I just have links out to, so some of the examples in the book have data, and so I have those data files here. They're not easy to get out of the text, so I just made them easy to get. You just click on it, double click on it, grab the data. There we go, copy it, and we can put it in stackkey. So I'll do an example of that too in a little bit. and then we're going to use stackkey's bootstrap confidence interval tool, which we'll get to in a few minutes. And then there's videos that go over all of this stuff too, so this is going to be slightly repetitive if you've already watched the first video that I posted here. All right, so notebook, what are we doing? We are now jumping into a branch of statistics called inferential statistics. And inferential statistics is where we try to draw conclusions about a population based on a sample. So just some things we covered back in chapter 1, we have populations, which are hard to get a hold of. So we use samples to try and figure out what's going on with populations. Statistic is a calculation you make based on a sample. So although we use the word statistics to cover a broad subject, this one that we're covering here, the word statistic, its most basic meaning is a calculation based on a sample. That calculation could be an average, could be a median, could be a standard deviation. It could be a proportion, which is like a percentage. And then we use those statistics to try and predict things about a population parameter. Okay? So based on a sample, we say, hey, this sample looks like blah, blah, blah. And so we think that's true for the population. Okay? Since we can usually not get a population, and I'll give some examples of that next. So sample statistics, calculation based on a sample. Population parameters are facts about a population. However, since we can never get the whole population, we can never know those facts for sure. So we have to make these estimates. So sample statistics estimate population parameters. Some examples of this. Average age of first heart attack. For men, it's about 65. For women, it's about 70. And I've been thinking about this one a lot because I recently lost a relative who had just turned 69 to a heart attack, and it came, we felt, out of nowhere. Like we didn't know she had any heart disease. And then she had a heart attack and died immediately. It was crazy. So I'm looking up some data on that. Just, for my own family's benefit, so they can know more about how to have a healthy heart. And it's a pretty undercovered thing in female health. There's a bigger focus on men with heart attacks, but it's a bigger killer for women. I think 1 out of 5 deaths of women is because of heart disease. And so it's something that needs more attention in the American healthcare system. Average salary of a public school teacher, that's around $60,000 last year. And so that's, new teachers and old teachers. Average salary of a new teacher around now is about $30,000. So unfortunately, being a teacher doesn't pay very well at first. Eventually, it gets a little bit better. But compared to other jobs where it's an important job, it doesn't nearly match up. Okay. Standard deviation of COVID-19 incubation time, we'll take a look at that one today. I've seen estimates that's around 2.4, 2.5 days. Standard deviation, the mean is about 5.5 days for the incubation time. We'll look at that in a minute too. Percent of women with higher education degrees, it's believed to be 36%. Now, is it possible for a group to find every adult woman in the United States and find out if they have a degree or not? Turns out that's not an easy thing to do. And even when we do the census like we're doing this year, and census means, unlike a sample, a census means get every single individual of the population. That's literally what the word means. So when the US does their census, that means they're trying to contact every single person living in the United States this year. And that's a huge, huge task. What's the population right now? It's like, are we around 400 million? I forget. Let's look that up quick. Just for fun. US population. Oh, I was way off. 328 million. So that's still a lot. It's 1/3 of a billion people live in the United States. That's a pretty big number. Now we're trying to reach out to every single one of them. Now, granted, we do so by family group kind of, and so I filled out the census for my family, so they got information about me and my wife and my 2 daughters in one shot. How many teachers do you think there are in the United States? Well, let's think about that for a sec. There are almost 330 million people in the United States. About 20% of those are school-aged kids, and maybe class size, let's say the average is 25. That's probably a little low. It's more like 30 students per teacher. So if we take 20% of that 330,000, and then we divide by like a class size of 30, that's going to be like 2 million-ish teachers, I think. So 300, see, 330. So that's a little overestimate of the US population times 20% is about school-age kids, and then we divide those school-age kids into groups of 30, so there's one teacher per 30, and that gives us 2,200,000 teachers in the United States right now. Rough guess, right? Is it easy to grab all of their salaries and get information about each and every one of those teachers? The answer is no, even though that is public record, somebody has to get all of those public records. Okay, so imagine it was your task to contact every single school in the United States. Oof, that's a rough job. People get paid to do that kind of stuff though, because we want to learn more about the population so we can improve stuff. Percent of women with higher ed degrees, okay, COVID-19. All right, so these are just some examples. Now, notation, this notation is important because you're gonna have to write to me about this stuff. When we're talking about samples, which is where this data came from, the notation for the average is an X with a bar over the top, okay? X bar means average of a sample. $60,000, that would also be an X bar. Standard deviation, if that came from a sample, that would be the letter S. If it's a percent from a sample, that would either be like a P for percent or proportion with a little prime on it. Sometimes in the homework, you might see P with a hat over the top. These both mean sample proportion or sample percent. Okay? As far as the population goes, which is what we're trying to predict, we use different notation. The mean of a population is the letter mu. Okay, so it looks kind of like a cross between an M and a U. It's a Greek symbol. So this would be a mu here because we're trying to figure out it for all teachers. The actual standard deviation for incubation times, that means we have every COVID-19 case that ever existed or will exist. Ain't possible. But if it did, we would call that one sigma. And these letters are going to be used in the homework, when you read the book, when you communicate to me. And so we got to keep straight when we're talking about a sample, standard deviation S, versus population standard deviation sigma. If we're talking about a population proportion, we would just use the letter P. P prime means it came from a sample. P means it's our belief about the population. Anytime we have something about a population, it's always a belief because we never know the whole population. Okay, it's a guess. When we have beliefs and we make guesses, there's always error involved, right? We never know for sure. If you don't know for sure, there's error. And so we need to try and measure that error. And that's what this chapter starts off with. How do we measure the error in our estimation when we're trying to use a sample to predict a population? Okay. Whenever I use a sample number like the mean, the standard deviation, or a proportion from a sample, these are what are called point estimates, okay? Because on a number line, right, if this is 30% over here, and this is 40% over here, then there's a specific mark on this number line or out here where 36% lives. And so that is called a point estimate because it is a single point on a number line of all possible, many different points. Is the population going to be exactly the same as what our sample came up with? And the answer is, for the most part, no. So what we do is instead of saying, hey, we believe it's 36, what we say is, well, it's somewhere between 30 and 42 maybe. Okay. So instead of point estimates, we say, yeah, it's somewhere in this window. Okay. And those are called interval estimates. And that's where confidence intervals come in. Okay, looks like we had some more people jump in. Hello, Jennifer. And is that it? April, I don't believe I got to say hi to April yet. And I'm pretty sure, did I say hi to Justine before I did? Yes, Dakota, Jenna, all right. So this is where the idea of a confidence interval comes into play. And so a confidence interval is a type of interval estimate. So it's an interval estimate for a population parameter. incubation param. In response to, say, a point estimate, I sent out a note earlier that said the incubation time for COVID-19, so average. So if I say X bar is average incubation time, let's be more specific than time and call it days of COVID-19. There have been several studies on this. One of them predicts that the average is 5.5 days. And so we're saying we think that that's true for the whole population. That if we could measure everybody that had COVID-19 and how long from their infection, whenever we know they were exposed to when they started showing symptoms, on average, we believe it's 5.5 days for everybody. Now, averages shift because new data comes in all the time, right? The world is complicated and moving all the time. So you can't really pinpoint the actual population mean. So instead, what we do is we say, well, actually, we believe the mean incubation period or time is between, and we give a range of numbers instead. And let's see, I made a note on that somewhere. Where'd my notes go? I believe it was 2.2 to 11.5, yeah. So we believe the mean incubation period is between 2.2 days and 11.5 days. And so this is what we call an interval estimate. Now, if I were to graph that out, let's try to do that on the next page. So number line. And then let's say, where's my pen? If we go every other one, so I need to get 2, 4, let's go 2, 3, 4, 5, 6. Should make a note that that's 5. Did I do that right? 2, 3, 4. Oops, I missed. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 right there, 10 right there. Okay, so what did I read in a recent study? That their window, their interval for the incubation period of COVID-19 was from 2.2, which would be about here-ish, up to 11.5, which would be right there. And they claimed the mean was 5.5. Now, usually the mean is in the middle, exactly in the middle. In this case, it's not, because there's different things they believe about the incubation period as far as its distribution. They believe the distribution is skewed right and not normal. Normal, if you remember from before, we talked about the empirical rule, and with the empirical rule, then we believe that it's symmetric about the middle. And notice this one's a little bit skewed right. So current research shows the incubation period to be skewed right. And remember, the skew is always to the tail. And so that, if I were to like draw a histogram over this, what we would find with a histogram is that there'd be some stacks over here that are moderate, and then they get bigger as we approach the mean, and then they start to taper off. And so there's a tail out here. So if you looked at a graph of the amount of time we thought it took the virus to incubate in a person's body before they showed symptoms, we would find the graph looks something like this here, where the mean is over here. Interestingly about this, the skew pulls the mean away from the median, and the median, based on the data, is believed to be 5.1 about, whereas this number right here is my mean X bar. Okay, this is my lower estimate for the incubation period, and this is my upper estimate for the incubation period. This picture right here would be a sample distribution. So if we took a data set that was accumulated by some researchers and we graphed the incubation times for every person, we would get a shape something like this. And it's believed, based on some experimental evidence also, that the population distribution looks like this too. So if we could actually get this for everybody on the planet to date, from whenever this started in what was it, December, November-ish of 2019, the population distribution should look different. Population, I mean similar. Population distribution. And again, what is a distribution? A distribution is a graph of the shape. That's all it is. So that means you make a histogram. So if we were to get everybody in the world and we knew all of their incubation periods, then we would expect the graph to look pretty darn similar. It would be exactly the same, no, but it would be close. And every sample we take would be a little bit different too. Remember, we talked about variation in samples way back. There was a critical thinking question on that. Now, as far as distribution goes, there's many different shapes, right? There's symmetric, skewed left, skewed right, and there's humpbacks and all kinds of wild stuff. Some of them have special names like Gaussian and normal and log normal. Some of them don't have names. It's just the way it is. There are three kinds of types of distribution in terms of this situation. There's the distribution of a sample, that's important. There's a distribution of a population. If we happen to know a population, we usually don't. So we use the sample to predict the population. There's a new type of distribution we're going to look at today, and that's called sampling distributions. That should be my next slide. Yep. So what is a sampling distribution? I'll tell you what it is not. It is not a sample distribution. Notice it says sampling. Distribution, i.e. a histogram of a single sample. Okay, like for example, 181 patients were, or actually 184 patients were grabbed kind of, I think it was a stratified random sample in China, and they tried to find the, when they got exposed, when we think they got infected, when they became systematic, trying to estimate this incubation period. Of those 184, they were only able to estimate the incubation days for 181 of them. So a few of them, they just couldn't find enough information about their medical history and getting the disease to figure that out. And that often happens when collecting data. It's kind of fuzzy sometimes. So a sampling distribution is not a histogram of a single sample. It is also not a population distribution. What is it then? It is a histogram based on many samples, usually based on just the sample mean. Oops. But it could be for a sample standard deviation or a sample proportion. So a sampling distribution is often a distribution of sample means for us, that'll happen most of the time, or it could be a distribution sample proportions. I'm going to try to illustrate that now to get an idea about what it is. So to do that, I'm going to go over to stackkey. Feel free to join me if you wish. Let's see, has anyone else joined us? I don't think so. Show desktop and stackkey. Why don't I have links to stackkey? Oh, they're on the previous page. So I have links to stackkey on the previous page. You could just search for stackkey. I'm going to jump over here. The places we're going to play with this week are mostly bootstrap confidence intervals, and I'll explain bootstrapping in a minute, for means or for a proportion. Now this one also does median and standard deviation. That's not in this course. If you took a second course in statistics, you'd probably get to those there. And a lot of this other stuff. And then sampling distributions down here. So I'm going to first do a sampling distribution, then I'm going to go back and do a confidence interval. So in stackkey, I'm going to sampling distributions for a mean. And then they have some data here. Now, the data they have here is different than the other data sets they have. Their other data sets are samples from different studies. These are actually populations. So for example, this first one says % internet access. And after doing a little research, I looked up what these numbers mean. And let's see, the World Bank does all kinds of studies across the world. And one thing they looked at, and this was a study from 2015, is they did samples in each country to try and see what was the percentage of people in that country that have internet access. So in Afghanistan, about 6% of people had internet access. If we scroll down to like the United States, and these are every single country in the world here. United States, 84, in 2015, 84% of people had internet access. And so like around 15% did not have internet access in the United States. It's probably way higher now, in the 90s is my guess. United Kingdom, almost 90% of people had internet access. Some countries had, a lot of people had internet access, other countries they didn't. So this is actually a population. Every country in the world is represented, and an estimate for each country of % internet access in that country. So this is more than a sample, it's a population. And over here is a graph of that histogram. Notice what the graph looks like. This is a population histogram. Now, what I'm going to do here is I'm going to generate one sample from this population. It's picking a sample size of 10 here. So we have a few more buttons to pay attention to, and we'll get used to this. So I'm just going to pick a slightly bigger sample size. I'm just going to go with 20 just for the heck of it. Okay. And so when I hit generate one sample, what's going to happen is it's going to, like, this is a deck of cards right here. It's going to shuffle the deck, and it's going to whip out 20 cards. And then it's going to plot those 20 cards for me down here. And then over here, it's going to say, hey, here's the average from that deck. That draw of 20 cards. Okay? So this point here is the mean of this sample right there. And if I do another random sample from this population, and it's just doing a simple random sample. Remember we did that way back in week 1. So I'm going to generate another sample. And I guess it ended up here. And if you click on that sample, it'll show you its sample distribution. Okay, so here I have a population distribution of 203 countries. Here I have a sample, 20 of those countries, and here's the distribution. Here's the other one. If I click on it, you'll see it change shape slightly. Okay, here's the second one. There's the first one. They look pretty close, but they're not exactly the same. Notice the second one has a stack of 2 by 25, and the first one has a stack of 2 near 0. Okay, so they're not quite the same. And I can keep generating samples all day long. And again, what it does is it just takes that full deck of 200 of these countries, shuffles the deck, and randomly draws. In this case, I'm asking for 20 cards. So every one of the dots here is a new sample. They might have some of the same countries, and they might not. It just depends from up here. So this is getting at one thing. We talked about the idea of sampling variability. Okay, so data variability means that, hey, not all the numbers are the same in that sample. Sampling variability means that any sample you take from a population is going to be slightly different from every other sample. Okay, notice each of these samples has a different mean. So now what I'm going to do is I'm going to generate a hell of a lot. Like I could generate one sample at a time all day long, and you'll see new dots appearing down here. I could generate 10 at a time. So then what the computer does is, again, it just shuffles the deck and 10 times draws 20 cards, okay? So basically what's happening there is it looks at the cards after it draws 20, writes them down, then puts all the cards back in the deck. So at every sample it makes, so right now I'm up to 19 samples. Each of those 19 samples was drawn individually from that 203. I could generate 100 and another 100. So up here, you can see, so I have 3 different graphs here, and I'm trying to remind you there's a difference between a sample distribution, that's one sample, what do the points look like if you make a histogram? Population distribution, if you happen to know everything about the population, what would its histogram look like? And there's that histogram, right? It's not really symmetric at all. It's not uniform. Maybe we'd say it's skewed right. Maybe it's good. I guess the mode might be over here, 1.1-ish or 4.5-ish. They both look about the same size. And this over here is the sampling distribution, which is a whole bunch of sample means. So every one of these points here is the mean of a sample of 20. So far I have 219 samples of 20 from this deck of cards. And I'm gonna start generating thousands of them. So every time I click generate 1,000 samples, so I've now made, with this computer's help, shuffling this deck of 203 cards, 2,219 samples. And every point on here is only the mean of that sample. And so if I point to a point, on the right here, it shows what that sample looks like. So over here, I can see those guys, since they have a higher mean, have more countries with big numbers. And if I pick a sample over here, I can see, since that mean is low, they must have more countries with people with not a lot of internet access. And again, remember my data here is percent internet access in a given country. So percent of people in that country who have internet access. And I'm up to 2,000. I'm gonna get like 8,000 samples. This program, right, by the way, runs on your computer. So what happens when I go to this website, my computer downloads the software without me knowing it. It's safe to generate these graphs, to run these sampling distributions. And sometimes it can like slow down your computer. I have an old laptop that the fan would be cranking wicked loud right now, trying to keep up. All right, so I've got 7,200, one more time. Come on, you can do it, 8,000. All right, so I have 8,000 samples. Notice the shape of the sampling distribution. And this is kind of interesting. When you take a distribution of sample means, which means you have a ton of individual samples and you only plot the mean, right? You forget about all the rest of the numbers. Those distributions for the sampling distribution of samples tend to be symmetric, which is kind of interesting. And the mean of the sampling distribution tends to be pretty damn close to the mean of the population. The mean of the population here is 43.24. See it flashing over there on the right? The mean of the means of the samples is 43.025. Pretty damn close to each other. So what we're going to do is we're going to use these computer simulations to help us figure out what's going on in a population based on repeated sampling. So instead of taking one sample of 20 people, we're going to take thousands of samples of 20 people over and over and over and over again. And then we get a better picture of what the population is like. Okay? So that's kind of the goal here. This is a relatively symmetric bell-shaped curve, which means the empirical rule should hold. So if I look within like 2 standard deviations on each side, which is what they give me when I first push the 2-tailed button, 95% of all the samples should fall between these 2 numbers. So this is basically making a confidence interval. So this simulation is saying, well, we think the average amount of people on the planet by country that have internet access is about 43%. So on average, about 43% of the citizens in any country should have internet access. Okay? Some countries have more, some countries have less. This is the average. Okay? But we never know for sure because populations are slippery. And so the interval is we're saying, well, actually the average percent internet access is somewhere between 31% and 56%, somewhere in there. We don't know exactly where. Okay. How sure of you is it in there? Somebody might ask me. I'm kind of like 95% sure the actual mean is in there. So we're going to start making some confidence intervals right now, for real. So again, this was the point of a sampling distribution. It might sound like nonsense at the moment, but you'll get used to it. So again, we have 3 different kinds of distributions aside from shape. We have the graph of a sample, that's a sample distribution. The graph of a population as a histogram, that's a population distribution. And then if we take repeated samples thousands of times and we plot only the means of those samples, throwing out all the rest of the data, we get what's called a sampling distribution, which is a distribution of sample means in this case. All right, so back to the notes here, and I think I'm out of pages, so let's grab an example. Show desktop. Let's go back to the stackkey homepage and build a confidence interval. So we're going to start off with means. So I'll show you how to make a confidence interval estimate for a mean, and let's go with the body temp data for now. Yep. All right, so I'm going to use the body temp data. Actually, I already think I did that one in the video. Let's go with restaurant tips then. Sure. Okay, I'm pretty sure I didn't do this one in the video. So here's a graph. So let's see, I'm trying to remember this data set here. This data set is from a particular restaurant, and throughout a period of time, they randomly grabbed some orders and found out what the tip was. And so after they got, they did that for like a week, they had 157 random samples of meals and tips, bills and tips from a restaurant. And so here you can see the tip plotted for that sample. So then what we're going to try and do is we're going to try and, so if you're the owner of this restaurant and someone's applying and you want good help, then the waitress or waiter says, the future waiter or waitress says, well, what's the average tip like here? And you can say, well, we have a good estimate of that. So according to this, the average tip for an individual meal is $3.85, okay, on average. Sometimes it's more, sometimes it's less, okay? It's skewed right, so rarely do you get high tips, but most of the tips are around $4, say. Now that's just this sample. So how do we turn this into a prediction for the population? All possible tips in a restaurant for a year or two. So then we have to make an estimate. So right now we have what's called a point estimate. The point estimate is $3.85 when we round that. So what we're going to do is we're going to start generating samples. So I'm going to do it like I did before. I'm going to make 1. And what happens here is a little bit different than before. What the computer does is it takes this 157 tips and it makes cards for them. And then it shuffles the deck. And so for this sample here, what happened is it shuffled the deck, it looked at a card, wrote it down, put the card back in. Shuffled the deck, looked at a card, wrote it down, put it back in. So 157 times it shuffled and drew, replacing the card each time. What's going to happen then is some cards won't get picked and some cards will get picked more than once. So you get a slightly different sample, but notice it looks pretty similar to the original one. Okay? This time the average tip was $4. So what they're trying to do is say, well, let's just assume that most days or most weeks are pretty similar to this one. Let's try to replicate that by just randomly reshuffling the deck and drawing the cards and see what happens. And so they just do that over and over and over again. So you could do that one at a time if you want. And every time you do that, you get a slightly different sample. And you can see all the means being plotted down here. So we're building a distribution of sample means. Every point here is the average of some sample. If you click on a different point, you get a different sample. All those samples, however, are based on the original. So this is super important. The original sample has to be a good random sample. We hope it's representative of the population. There has to be randomness involved. Maybe it was a simple random sample. Maybe it was a stratified. Maybe it was clustered. Maybe it was systematic. Maybe it was some other method. But it has to be a good random sample. If this isn't a good random sample here, then all the work we do here is crap. So assuming we have a good random sample, we can use this computer simulation to make up new samples based on it. And what we really want to do is do thousands of them. Okay, so I'm just going to get up to, usually I want over 6,000 to get an estimate of what's happening with the population. Okay. All right, so I just did 7,007 samples, and it's got some other numbers up here, the mean of this group of means. So again, every one of these points is the average of 157 tips from like a different day or a different week, according to the computer simulation. Okay, notice it's kind of all over the place, but it doesn't stray too far. Notice that the average over here is 4.6. That's the highest one I see. But the average actual tip was like 15 bucks. Okay? And again, we're never going to see, imagine, shuffling, taking this deck of 157 and pulling out a card and it happens to be the 15. Then you put the 15 back in the deck and you shuffle the cards good and you pull again, it's a 15. And then you shuffle the cards again, you pull it out again, it's a 15. Right? That ain't going to happen. The chances of that happen are 1 in a zillion, whatever a zillion is. So once I have this right here, I then click to tail, and then I have to decide how many of these samples do I want to stick in the middle. The default is 95%, and I'll explain what that means in a moment. You could click on that and change it to 90%, but it's got to be a decimal. So I could put 0.9, and then it says, okay, let's put let's find the middle 90% of all of these averages. So if I do that, let's make a snapshot of this to compare it to another one. Snapshot. Add to, I don't know if I have a blank page or not. Shrink that down a touch. Okay, so that is a 90% in the middle. And back to desktop. If I switch that to 95, click here, 0.95. Let's take 95% of the samples and find out where they live. All right, notice with 95, this got a little bit wider because I had to collect more stuff in the middle. So if you made that 99, it would get wider still because it's only putting 0.5% of the samples in each tail. Let's go back to the 99, 95, comparison. And remember, in stackkey, the only way to get a graph is to do a screenshot of it. So I just want to confirm here. It's about the same size. That if I look for 90% of the samples, then again, it's less in the middle than 95%. Okay, so this right here says, hey, grab 90% of those samples. What lies on the edge of 90% on each side? Take 95% of the middle, and what numbers lie on the edge. So these edge numbers give me an interval estimate, and the center number gives me the point estimate. So there's a couple of things I can say about this, and I'll do some notation. So now we're actually going to do some confidence intervals. So confidence interval, and this is actually one of your homework questions too. And in this case, what we're trying to do is we're trying to estimate the average tip of a restaurant. Average tip at a particular restaurant. I forgot what restaurant this is. That's what we're trying to estimate. What symbol would that be? Well, that would be a mu because it's an average and it's the average of all possible tips. So that's the population parameter here. What I have right here is X bar is 3.851. And that's what I'm using to approximate that population. Again, this right here is what's called a point estimate. It's a specific number. Okay. And that's a lot like saying the average human body temperature is 98.6. If you take your body temperature every day, it's not always going to be 98.6. It varies throughout the day. It varies by the day. So again, it's a prediction of average, not an individual. Okay, so those are things we have to keep straight. We're not talking about an individual tip. We're not talking about the tip one waitress got. We're not talking about the tip of a particular meal. It's the average of all possible tips. We're estimating at $3.85, okay? Which is going to be similar to the original sample. So if we looked up that before, it was 3,845, I think. So it's similar. Now, the thing is, we never get it right because we don't have all the information. There's always an error. So another estimate we're getting over here is what's called an interval estimate. So we think the actual amount of tips is somewhere between 3.540 and 172. So this is what's called an interval estimate. Now this is the interval estimate as an inequality. Often we write it using interval notation. You'll see that come up in the book and in the homework, interval notation. So in interval notation, we would write parentheses 3.54 or 3.540, comma, then the upper one, 4.172. The margin of error, there's two ways to look at it. It's the distance from the center to the edge. And these are, in theory, symmetrical, but in practice, they're not. And I'm going to move this one to the next page. We'll do that in a sec. Repeat on that in a moment. So there's two ways to get the margin of error, three ways. You could subtract the middle number from the upper or the lower number from the middle, but the best way to do it is to find the distance between the upper and the lower and divide by 2. So in this case, to find the margin of error, and the margin of error is just the distance roughly from the center to the edge. Then take the high number, subtract the low number, and divide by 2. So in this case, my margin of error is going to be 4.172 minus 3.54, and then cut that in half. So calculator, 2. Parentheses 4.172 minus 3.54, close the subtraction, divide by 2. So parentheses are important there. I get about 3.16. That's about 3.16. Now, did I make a mistake there? It doesn't look right. 0.316, that's more like it. And again, always find a way to double check. So I was just looking from here to here. There's no way that's $3 to get from 385 to 417. So clean up 0.316. So a couple of ways to list the confidence interval. One way to list the confidence interval is to just use an inequality and say, hey, we think the actual mean is in between these two numbers. You might use interval notation. So when you're doing the homework, pay attention to whether it says, hey, enter it as an interval or enter using interval notation. I mean, inequality versus interval notation. We could also state it as the center and the spread. So another way to state it would be to put X bar in the middle. Oops. And then plus or minus your margin of error. And so for us, that would be to say, hey, the middle is about 385 plus or minus 32 cents, or more exactly 316 to 3 decimal places. Typically, we take the calculations to one more decimal than the data. The data was in dollars and cents, so I'm taking it out to the nearest tenth of a cent. It depends on the tools we use to calculate that, how much ability we have to do that. So if we take $3.85 and add 32 cents, we should get roughly the lower number. And if we take that middle and add it, we should get the upper number. So let's see how close we get. So if I take 3.851 and I add, let's subtract first. So you're going to do a lot of graphing and arithmetic, and the graph's done on the computer. All right, so subtracting here, borrow, we get 5, 3, 5, 4, which is pretty close to, what did I just do? I made a mistake. Oh, that's supposed to be a 3. 8 minus 3 is 5, 3 minus 0 is 3. Okay, so we get about 3.54, which is what that says right there on the low end. If I take the margin of error and subtract, if I take the margin of, add the margin of error to the mean, adding, we get what? 7, 6, 8, 9, 10, 11, carry the 1, 4.167, which is relatively close. These are never going to come out perfect because they're computer simulations. Notice that graph is a little funky, and that's okay. It's not perfect. It's always a little wonky. So one last thing about this is how do we use the 90% with this? Because somebody says, hey, can you estimate the average amount of a tip? And I can say, yeah, it's somewhere between $3.54 and $4.17. And this 90% in the middle is what's called a confidence level. So in this particular case here, a confidence level is 90%. And confidence level is confidence in the process. It is not the probability that I'm right. I don't know that. Probability and so putting this all together, I would make a media statement, as the researcher for this restaurant, and I would say, we are 90% confident that the average tip is between $3.54 and $4, and I think then rounded to 17 cents if I put in dollars and cents. Okay. Another way to state that is, so alternative approach would be, instead of writing it as an interval, to talk about the mean and the margin of error. Oh. Alternatively, we could say we are 90% confident that the average tip is within, let's see, what was my spread there? About 32 cents and 3.85 is within 32 cents of 3.85. Okay, so the within talks about the spread, right? That's that plus or minus within. So I'm within 32 cents of 3.85, somewhere in that range. So a couple ways to express that. Are there other ways to write that in English? Yep. And then we got to get used to what it means to be confident, and we'll just have to take time throughout this week to do so. So this example here was like, what's it, number 12 and 13 in the homework maybe, or 12 and 14, somewhere in that range. So you definitely want to try that on your own, see if you come up with similar results. Practice. Continue. 6. Yeah, so number 6 says, hey, go to stackkey and check out their data on restaurant tips. And I have a link here to get there. And then run a simulation to see what you get. So last time I ran it, I blew this up a little bit, I got slightly different numbers, but pretty similar. I got 3.542 up to 4.167. And if we round those, that's the 354 to 417 is what the tip is. And I say do at least 6,000. Other problems here, sometimes you have to copy the data in, and we've played around with copying data, so just be careful when you do that. You should just be able to highlight the data, take it to stackkey, choose edit data, and just delete whatever's there. And the important thing here is when I paste it in, each number is on its own line, and there's no extra space after them. I don't have a header row. Otherwise, it'll call 33.2 the header, and it won't use it as one of the numbers and totally mess stuff up. So double check that you have those correct. So I'm going to click OK. I'm on the confidence interval for a mean page, which is where I need to be because I'm trying to estimate a mean, and then we just run thousands of samples. And so the two hard parts, one is get to the right page to run your samples and push the right buttons. That problem asked me for what, an 80% confidence level. So I would want to change this to 0.8 for 80%. And then this is the confidence interval right here, from here to there. That number's the low, that number's the high. If it asks for a margin of error, then you're going to have to subtract and divide by 2. So sometimes you have to do arithmetic. The hard part then is interpreting. What the heck does that mean? And I'll be talking about that every day this week. And it does take getting used to. The steps for doing that are listed in the methodology page. So all the stuff I went over today is in the pre-recorded videos in the video section. And then I made a bunch of written, typed up notes related to the stuff I just went over here. So what do all these buttons do for us in stackkey? So I give some examples of that, describing what I did earlier. How do you interpret what a confidence interval means? So you got some numbers here. What the hell does it mean? And so here I kind of break it down for a body temperature example from their data. And the next page is the steps you have to go through to create a confidence interval based on some data. So I have links to the page, what the screens look like, explanations of what you're supposed to do, what buttons you push, and then what to do after to get the results. And the ones we did today are based on this first part using a mean. And then this week we'll also do proportions. So that would be like the percent of women who have college degrees. Anytime we want to know some percent of a population. And that's a slightly different, it's a different page you go to, but the process is the same. Okay, so that took about as much time as I thought it would. Does anybody have any questions? Mostly I think you just need to go read and watch videos and then try some problems. But definitely don't forget, as the link shows for the textbook, you're going to use my version of the book, not the web book this week. No questions in the chat. So again, definitely want to use my marked up version of the book. That deletes some stuff temporarily, highlights some stuff. And then if you want to try any of their examples where they do calculations, even though I cross it out, I have the data in this some data files page here that you could play with if you want to try to follow along with the examples in the book.